Welcome back to our second segment. We're still looking at solving circuit problems. Now we want to focus our attention on questions that are structured, the long questions that you typically find in section B. We'd also share some tips in terms of how you approach the question. But also very important, when you read the background or the context of the problem or the question, the scenario, make sure that you read it with an intention to understand before even looking at what the questions are really asking you. Understand first, highlight the keywords, because for every information that you are given in a long question, there is always that part that I'd want to think of as a catch. Once you get the catch in a question or something that's unique about that scenario, then you are able to appropriately use the correct, approach or method of solving that particular problem. Let's look at one example here. It says here, the circuit alongside, that's the circuit that's provided, consists of a 6 ohm and 15 ohm resistors that are connected in parallel. So the two resistors that are given are the 6 ohm and the 15 ohms are in parallel, okay? Now a resistor of an unknown resistance R, okay, there is the resistor of unknown resistance R, okay, is connected in series, okay? So R is connected in series while the 6 ohm and the 15 ohm are connected in parallel. Now the resistance of the battery and the connecting wires can be ignored. What does this tell us? It tells us that the battery and the conducting wires have negligible resistance, okay? The total power dissipated by the parallel part of the circuit is 50 watts, okay? So the power for both circuits combined, for both resistors combined, which is the 6 ohm and the 15 ohm, is actually 50 watts, okay? Now the first question says, define the term power, right? So when you talk about power in the context of electric circuits, okay? If you talk about power in the context of electric circuits, what are you talking about? Power is actually the rate, okay, of energy transfer, energy conversion, or energy, transformation, energy transformation, okay, in a circuit, okay, right. So even if we go back to our data sheet, you'd realize that this is the power definition that we talk about. So W is energy or work, all right? Right, and then we also have time, okay? And then we talk about, when we talk about time, we're talking about the SI unit, which is the second. So the data sheet becomes a valuable, resource in terms of that, okay? So we understand that power is the rate of energy transformation in a circuit, or work done, because when energy is transferred, work is done. And then we also go on and say work is equals to change in energy. So work is energy, energy is work. So this is the main concept regarding work and energy. But again, we say that we can say P is equals to W over delta T, right? Okay. Now, the resistance of the battery is ignored. Now, the follow-up question says, calculate the effective resistance of the parallel combination, right? If you look at that, we are talking about these two resistors, okay? What is their combined resistance, okay? Again, if we go back to our data sheet, okay, you'd realize that for a parallel circuit, this is the formula that you need to make use of. But if there are two resistors in parallel, we can use even the product over sum, okay? So R parallel, okay, is equals to, we have the product, let's call this R1, okay, and then this one R2, 15 ohms R2, okay, and then we would have, let's say, R1 multiplied by R2 divided by R1 plus R2. So this is actually applicable when only two resistors are connected in parallel. But if it's a combination of more than two resistors connected in parallel, this formula may not be used, okay? So we've got R parallel, okay, is equals to 6 multiplied by 15 ohms, okay, divided by the sum of those two, 6 plus 15, right? Now, there's something that you need to realize with the parallel combination of resistors. The more resistors we connect in parallel, the lesser the equivalent or the effective resistance of that combination. So in this case, the smallest resistance is 6 ohms, okay? Now, if we calculate or determine the total resistance or the combined resistance of the two, actually what must happen, the combined resistance must be less than 6 ohms, which is the smallest resistor. That's one way of verifying that. Okay, so if we go to our calculator, then it follows that we have, okay, it's a fraction. Okay, R1 is 6 times 15, okay, and then at the bottom, at the denominator, is the sum of those two, 6 plus 15. Okay, so our effective resistance is 30 over 7, which gives us 4.29 ohms. And 4.29 ohms is actually less than 6 ohms, which says then our answer is correct in this way. That's one way of verifying. So it's 4.29. Okay, so this is RP is equals to 4.29 ohms. Okay, right. Let's go to the next question. The next question says, calculate the potential difference across the resistors in parallel. Right. So this question is actually 3 marks. So this is what I would want to think of as a routine calculation. Right. So we are given the power, okay, of the parallel combination. So if we are to do that, we can use the power formula because we've got the resistance of the parallel combination. And what are we looking for? We're looking for the voltage. So the formula is P, okay, is equals to V squared over R. So this is R parallel, okay, that we're using because it says for the resistors in parallel. Okay, so the 50 watts is for the combined power rating of the two resistors, which gives us 50 watts, okay, which is given, then V squared. The resistance that we got for those two, we are going to use the solution from which is 4.29, right? So we'll do that substitution, 4.29, okay? So that's the resistance. So we're looking for voltage. Okay, remember that is V squared. Okay, now we have done the substitution without even trying to isolate V. Okay, so we'll do the calculation so that we get the magnitude of your voltage across that parallel combination. Okay, so we are saying on our calculator we have got 50 multiplied by, we've cross multiplied with the resistance, which is 4.29. Okay, 4.29. Okay, that gives us that value. But remember, this is equal to V squared. Okay, so for us to get the V, we need to find the square root of that value, okay, whatever that value is. So our voltage across the parallel combination of resistors is equals to 14.65, okay? It's going to be 14.65 volts. So we can think of this as V parallel because that's what the question wants from us, okay? Now, in the next question, they want us to determine the current passing through resistor R, okay? They want us to determine the current passing through resistor R, right? So what do we know? We know that the total current passes through, you know, the two resistors, which is the 6 ohm and, you know, the 15 ohms, or the total current rather is split between those two. So if we can find the total current in the parallel combination, it's exactly equal to the current that passes through R, okay? So we are saying that the total current, which is the main current, is equals to V parallel divided by R parallel, okay? Because it's a 3-mark type of a question. It's the formula, in this case, which is the Ohm's law, the substitution, and then the correct answer. So the total current is the current that passes through R, okay? Which is current through R, okay, is equals to our V parallel. We managed to get a value of 14.65 volts, right? So that's 14.65, okay, divided by R parallel. What did we get for R parallel? We can quickly verify that value. For our R parallel, we get 4.29 ohms, okay? 4.29 ohms, 4.29 ohms. So this is the current that will go through resistor R. So that was the thinking. Now we go to our calculator, right? We've got 14.65, okay? We divide that by the effective resistance of the parallel combination, which is 4.29, okay? It will give us the magnitude of the total current in this circuit, which is 3.41 amperes, right? So that gives us 3.41 amperes. This is the total current, okay? So this 3.41 amperes is split between 6 ohms and our 15 ohms. So, but it's all the current that goes through resistor R. So it's very important for us to take note of that. Right, okay, moving along. Now, the same circuit, we're still looking at the same setup. It says here again, the total power is still 50 watts, okay? Now, the switch in the circuit is now open. This is the switch, okay? What does that imply? If we open this switch, let's call it switch S for now. If switch S is open, okay, what's going to happen? It will mean that there will be no current flowing through the 15 ohm resistor. So the only resistance that we have left now is actually the 6 ohm and R, okay? So we have got two resistors that will be connected in series, okay? All the current passes through R and all the current passes through 6 ohms. Now, let's go back in terms of understanding the parallel circuit. The fewer resistors we have, or no resistors we have in parallel, the greater the effective resistance in the circuit, okay? And how does that affect the current in terms of the Ohm's law? Maybe that's the kind of thinking that one must assume. In this case, we are saying, okay, if we open switch S, okay, we won't have a parallel combination of resistors. It means, number one, let's appreciate that the total, resistance in the circuit increases, okay? So if the total resistance in the circuit increases, what does that mean in terms of the current, okay? Total current will decrease. Okay, so we're saying the total resistance increases. Very important to mention that it increases, not just changes, okay? It increases. So we know from Ohm's law that current and voltage are actually, directly proportional. So if the current decreases, that will also have an effect on the voltage because V is directly proportional to I, okay? So a decrease in current will be accompanied by a decrease in voltage. So the voltage will decrease, okay? So if the voltage decreases, it's based on the Ohm's law. So in other words, if we are to work backwards, okay, we are saying that the voltmeter reading V will also decrease, okay, based on the fact that removing the 15 ohm resistor from the equation says to us that the effective resistance in the circuit will increase. That will effectively decrease the total current, meaning also the voltage will have decreased, which justifies our choice in this case. So these kind of problems that have to do with the, thinking and applying, they require you to understand, each part of the question clearly. Because when we open the switch, how does that affect the total resistance? Now, if resistance has increased, how does that affect the current? And you are always supposed to respond to these, type of questions that involve explanation. You need to use, simple facts. You don't write a long essay. Just be straight and short and brief to the point, because it says for any case, a question which requires, explanations, you need to be brief on that. Okay, right. Okay, and then this other question says a geyser labeled 2,000 watts. Okay, on average uses daily 5 hours. It's used daily for 5 hours. The cost of electricity is 80 cents per kilowatt, okay? Calculate the cost of electricity for using the geyser in a 30-day month period. Okay, now we know that when we talk about, you know, the energy consumption, we are saying that, you know, the cost of using electricity is equals to the unit price, okay, which in this case we are given multiplied by the kilowatt hour, okay? Right, so this is what we have here. And when we talk about a kilowatt, we are saying that 1 kilowatt is actually equals to 1,000 watts, okay? So energy consumption is always in kilowatt hour, okay? So if we have got 2,000, it means there are 2 kilowatts, okay? So in this case, we are going to say cost is equals to, that's the 2 kilowatt, but the price is given is 80 cents, okay? 0.80, which is 80 cents. How many kilowatts are there? It's 2. The 2 comes from the 2,000. So 2,000 watts is 2 kilowatts, okay? Multiplied by, you know, the amount of time that you use per day, and how many days do we have in that month? If per day is 5 hours, it means we've got 35 hours in a 30-day month. Okay, so then our cost becomes, if we can go to our calculator, you'd realize that we have, in this case, it will be 0.8, okay, multiplied by the 2 kilowatts, which comes from the 2,000 watts, multiplied by the 5 hours that is used, the duration per day, and then in 30 days we multiply it by 30, okay? So this is actually 240. Actually, this is in rands. So this value is actually in rands. So the cost for using it is actually 240 rands. Okay, it's 240 rands per month. So that's the cost of using the geyser for that period of 30 days. Okay, so these are some of the questions that you must expect in terms of circuits, you know, energy consumptions, which has a lot of application, which makes us to think about the ways of saving, you know, electricity given the current scenario that we find ourselves in. In the next segment, we'll look at more circuit problems and explore the Ohm's law and see how these concepts comes together. Let's take a short break for now.